Okay, welcome back. Um, so the topic for today, we are going to write a lot of code for reinforcement learning. So I'm gonna do a little bit of a recap from last time. Um, so in reinforcement learning, we have two main parts. The first part is the agent. Uh, this one is the agent. And the agent is basically the brain, the one who will make a decision. And another part is the environment. So the environment will be the world that you will interact with. And whatever action the agent does, the environment will return the observation along with the reward, right? So the agent will use the observation and the reward to make a new decision. So we will have this loop to keep in mind. So the first thing that I want to note is that in a lot of reinforcement learning, um, you might have to only write the agent. In some problem, you have to write the agent as well as the environment. And for today, I will only focus on the agent. Basically, we will use the available environment that someone has already coded for us. So we don't have to worry about two things. And to write an agent, it also depends on the environment that you interact with. You write a different agent. So it's not the same. So the structure is similar, but the actual detail will be different between each of the environment. So let's start with we only use the environment, and one of the popular library for the environment is called Gym. You use Google search, you can have Gym environment, right? And this Gym environment, they will have uh, a lot of environment that you can interact with. Um, so the first one, we will use the blackjack. So if you're not familiar with blackjack, basically you play with a deck of cards, and you are dealt two cards, and the dealer will have one face up card and one face down card, right? And basically, who have the sum of two cards is higher who take the money. Now, because of this, there are some special rule, right? For example, ace can count as 11 or 1, right? So it can be count in both. For Jack, Queen, and King, you have 10, and then for the other number, you have 2 to 9, right? And the goal is to have the higher sum. However, if you go exceed 21, right? For example, if your sum is 22, you are busted and you will lose immediately. And for the dealer, right? For the dealer will keep drawing a card until the sum is 17 or greater, and then he will stop. If the dealer bust, it means that if the sum of the dealer is 22 or above, then the player will win. And if the another player bust, then the outcome is decided whose sum is closer to 21. So that is the rule of blackjack. So have you played blackjack before, or maybe heard of the word blackjack, right? So hopefully, okay. So we have, so they create this environment for us, so we don't have to write a code for like shuffling the card to deal the card and so on. And what we have to pay attention to is there are two things. First is the action space, right? So in our diagram here, uh, right, the agent will have to do the action, and the environment say that, well, you have two options. right? For the action space, you have two options, and the action space is to stick. It means that you don't want to draw anymore, so you send the value 0, or you hit, you will draw another card that will be 1. So you have two actions. And they also come with observation space, right? The observation space will have 3 number, right? So we have 3 number. So the first number is our current sum, the current summation. And the second one is going to be the value of the dealer face down card. And the last value is going to be either 0 or 1, stating that do we have S or we do not have S. So that is the observation space. So in gym environment, they already calculate the observation space to us. So instead of looking at this picture, they already transform this picture into 3 numbers. So we can use this observation, right? So basically is this part, the observation is this part is the 3 number, like X, Y, Z. That would be the one that we will use, and we will want to do the action in either 0 or 1. All right. So in Colab, the gym package, the gym library is already imported, so we can use it right away. So the first part, right? So remember we have two parts. We have the agent and the environment. Now we use the environment from gym, so we don't have to write a code for that, but we still have to write a code for the agent. So we will define the agent, right, that play Jim's blackjack, right? We want to define the agent. So to define the agent, right, we have to create a class for the agent, right? So just like when we create a class for neural network, right? So we have a class for the agent. So we have class, for example, blackjack agent, and this class you are going to write actually 2 or 3 function. So the first function is the initialize function. Basically, you have to define the agent, right? So we have the initialize function, and in the initialize function, you would want to receive the environment as part of the parameters, right? So when you create a backjack, you have to understand the environment. So you have to increase the element in there. And after that, right, you have to save the environment to your local variable, right? You save into the class variable. And then you would have to write what is the state space, right? So this is the observation space. So we can have environment dot observation space, right? And then self dot action space is also the environment dot action space. So this will give us basically it's going to tell us that okay, the state space will have 3 numbers. The action space will be either 0 or 1. So that is the information that we save that will be used later on. So this is about the environment that we have to save for ourselves. And then we have to have the learning part, right? The learning part. So if we use what we learned, we want to use Q learning. Let me see. Yeah, so it's basically this kind of equation. We want to have this kind of update equation, right? So basically we need to have we need to store this variable, right? You need to store variable, and the Q value here will take 2 parameters, right? The state parameter and also the action. So basically it will give you the score, right? If you give it a state, give you an action, it will give you a score, whether or not your action based on this state is good or not. So we have to write this queue, right? So we will say self.queue. Now, here I'm going to use a dictionary. So I have to import, right, from collection, import default dict. And I'm going to use this dictionary to define the queue, right? So it's going to be lambda default dict. No, not default dict. It had to be, I also need a numpy, right? Okay. So from import numpy as np. So what this does is going to give us the dictionary based on the action space, right? So this will give you how many action space do we have. It's going to create a dictionary that give the value 0. So this line, of course, basically, like whatever Q, SA will be equal to 0 for all S and Q and A, right? For every state, every action, you will get a 0, right? That is basically what it says. So we define Q, right? What else do we have to define, right? So we have to go back, right? In this equation, what else do we have to, we still need to have this gamma, right? This gamma, this is called the discount factor, right? So we have to define the discount factor. So we're going to say self dot gamma. You can pick any number between 0 and 1. I'm going to pick 0.95, right? So this is basically a discount factor, right? This will control how important it is for the future reward. So we need to specify the epsilon. So the epsilon is basically because when you want to learn initially, you don't know which action is the best. So you want to take some random guess at the start, and later on you would want to use the best action. So from last time we talked about this, right? We talk about the epsilon greedy policy, right? Basically, we have this Q value. For the probability with 1 minus epsilon, you would want to take a greedy action, and with the probability epsilon, you want to choose a random action. So we set the start of the epsilon to be 1, right? So this is for exploration, right? So if you start with 1, it will mean that it will always random. And we are going to have the decay rate, right? So the decay rate is basically what you want your maybe 0.95. So basically you want the epsilon to go down over time so that you make a better decision, right? So you don't want to making random decision later on when you actually learn a lot about the environment. And the last thing that we have to specify is the number of episodes, right? So let's say we have 1,000. So what is episode? What is the definition of episode? So in the blackjack, right? When you play one game from the start to finish, that's one episode. But within the game, right, you can make many decisions, and each decision we will call step, right? So in one episode, there can be many steps. So if I say episode equal to 100,000, it means that it's going to play the blackjack 100,000 games, right? So this is the initialize that you have to specify at the beginning. Okay. So now we define the internal variable for the agent. Now the agent have to make a decision, right? So we have to create a function that it can make a decision. So we could define the function called choose action, and the choose action will receive a state, right? So basically, you will give it what is the current state, and what you return, you will return the action, right? So we can say if numpy.random.uniform 0 to 1 is less than self.epsilon, right? So if we pick a random number between 0 to 1, and if it's less than epsilon, we are going to use the random action. So our action is going to be self.environment.action space.sample. So this will pick random action, right? With property epsilon, you pick a random action. But if not, right, we want to pick the best action. And the way to pick the best action, you will use the np.argmax, right? Basically, it will return the index with the maximum value, right? So we have the queue, our queue, right? And then we put in the state, right? So when you say queue state, what it means that it will give the value for every action, right? So here we define it to be QSA. So basically this will take, right? It will take the maximum, right, of all A in Q, S, and then something, right? So self.Q state is basically it will give the value of the from the Q table, from the Q array for every action for that state. And then you take the argmax, so you get the best action. And then you would return action. So this is the second function that you have to write, the function choose action, right? So basically you get the state, you get the action. So we have the definition, the choose action function. What else do we need? We haven't done this equation, right? We haven't done this equation at all. This is the update function, right? This is the update function. So we have to write the update function for the agent. And this update function is going to update the queue, right? To make it more accurate. So we have to write the next function would be the update function. And the update function will take multiple argument. It's gonna take the state, right? It's gonna take the action. It's gonna get the reward, and it's gonna get the terminated and also the next state. So what are all of these variables? So we are at this state. We perform this action. The environment give back the reward, and it will give you the next state, right? And the terminate here, it will determine whether or not the game end or will not end, right? So that is that are the meaning of these 5 variables. So the update, you need all of them to be able to do the update function. So we have all of these, right? So if we finish, right? If we finish the future Q value is going to be 0, right? Because there's no future, right? Because we end here. So the future is nothing, right? Because we finish, right? Basically, if it terminates, your next state is meaningless because there's no next state. You just end the game. So if the game end, right? So if the game end, um, there is no future, right? But if the game is not end, our future Q value is going to be the NP max of the self Q of the next state, right? So what does this mean, right? What does this mean? So in this diagram, right, we are in this state, right? We are in this state S. We perform the action A, you get the reward R, and then this one is the next state, right? So your future Q reward is the reward at this node. And this node, you can have many actions, right? You can have A prime 1, A prime 2, you can have many actions. So what would be the best representation of the value at this node? Basically, you have to look at all of the action and you can take the maximum, right? So that's why we say np.max, like you take the maximum value of the next state, right? Regardless of the action, you just take the maximum. So that would be your future Q value, right? So we have the future Q value. So we're gonna have the target, right? So we have the target Q value is the value that is the correct answer for this particular instance. So the target Q value is going to be the reward plus self.gamma times the future Q value. So what is this equation come from? Right? This equation is basically this equation. Right? So this is your target. Right? This is your current. Right? So it's basically so S prime is the future reward. Right? So because there is your action will make you will reach the next state without the probability. So this term it doesn't matter because we have a deterministic behavior. You make this action, you always go to this state. And this one is the policy. Now the policy is here when you don't know which action to take, but because we already have this action, this will become 1 for the action that we pick. So this equation will become the reward. Let me change the color. So it's become the reward, right? Plus the gamma times the future reward, right? So this equation will be only 3 parts. So this is your target, right? So when you have the target, it means that you want the Q, basically this is the target for QSA, right? But our current QSA and the target QA is not the same. So we want to, basically we want to have like this Q of state action to be equal to the target Q value, right? This is what we want. But if we just plug in that value, it's going to be too fast, right? Because at the beginning, you don't even know if this is the optimal value. We know that this one is better. So we want to move slowly, right? You want to move this value closer to the target Q value. So in order to move closer to the target Q value, we don't want to set it equal to the target. We want to set it to, so basically we want to add, right? So the difference between the target value minus self dot Q state action, right? So this equation is the same. You want to add the difference between the target and the state, right? So if I want to draw a picture, right? So you have the current QSA, it here. This is the target, right? The one that you just compute using the below equation. You want to set this value to be equal to target, but we will make it smaller, right? We want to move it a little bit closer, right? So we're gonna have some uh, some value, right? Some parameter to multiply the difference. So the difference is the arrow. So instead of just plus equal to this exact difference, we will add something called the learning rate, right? So we have the learning rate times this one, but we haven't defined the learning rate. So we have to go back to our definition and we have to set up the learning rate. The normal value is like 0.1, so this is the learning rate. So we don't want to set the new Q value equal to the target. We just want to move it closer to the target. That's why we have this coefficient. We have to have this constant to multiply the difference before we add it to the current Q value. So this is the update function, right? So far so good. So we have this update function. We have the choose action function. The last function that we have to write is basically the decay, right? Decay epsilon. So whenever you want to decrease the epsilon value, so we can say cell dot epsilon equal to cell dot epsilon times cell dot multiply. So you multiply the decay rate to the epsilon, and then you just keep multiplying every time you want to decrease the epsilon value. So this epsilon value, normally you will decrease the epsilon when you finish one episode, right? So this action, it will do the action, this one step. So after one step, we don't decay the episode yet until we actually finish the game, finish one game, and then we decrease the epsilon. Sometimes you don't want the epsilon to be too small. You want it to have some exploration later on. So you can set the minimum, right? So you set max between this value and maybe 0.1. So the epsilon will start with 100%, like 1, and it will go down, but it will not go down less than 0.1. So that is the meaning of the decay rate. Okay, so we run this block so that we have our agent defined. So every time you want to use reinforcement learning, you have to write the agent class, right? And then the agent class gonna have the initialization, the choose action function, the update function, and then the decay function. So now we are ready to train, right? We are ready to train. So we're gonna start with a new block of code. We want to create the environment, right? So we import gym, right? So we will use this environment, the blackjack environment. So we import gym, and then we say the environment equal to gym.make, and then you say blackjack version 1, right? And then there are some other parameter, right? Natural and SAB. If you go here, they will have the argument natural equal to false. It will give more reward, right? So the reward here, if you win the game, you get +1. If you lose the game, you get -1. If you draw the game, you get 0. If the natural is true, when you win the game, you get 1.5. But if the natural is false, you get just +1. So right now we are going to use the natural equal to false. So win the game, you get 1. You lose the game, you get -1. If you draw, you get 0. Okay? So we have the environment. We can create the agent object, right? So agent equal to blackjack agent. So we just write this class, right? We just write this class. So we use this class. And this blackjack agent, you're going to send in the environment. Oh, it's the big J. Okay. So now we create environment. We create the agent. So now we are ready to train, right? So to train, we can say, we can use the um, TQDM from the QDM, import TQDM. So the TQDM is basically is the visualization of the progress, right? When you do the loop, right, it will have the progress bar, like how many iterations of the loop that you have done. So it's gonna be a nice visual. You don't need it, but it will be nice to have. So we can say for episode, right? For episode in TQDM of the range of the agent dot number of episode, right? So we are going to play the game, whatever the number of episode we have, right? So we have 100,000, so we are going to play 100,000 game. So what happened in each game, right? So we're going to have the state, right? The state is going to be the environment dot reset. So you want to reset the game, right? It's basically you start a new game, right? You start a new game. So when you get start new game, and then we have the terminated equal to false, right? Because we just start a new game, so it's not finished yet. So we start with false, and then we will play until it's not terminated, right? We play until we finish the game. So what happened in each turn in the game? In each turn, you have to take action, right? So we say action equal to agent dot choose action, and then we will send in the state. So the current state that we get from the start of the game, you send this state to the function choose action, right? So we have this choose action function already, right? So we say agent dot choose action, and when we get the action, we can send this action to the environment, right? So we will have the environment dot step action. So this is how you send action to the environment. So in every environment uh, that you write or you use, there is going to be a function called step, and this function step will take the action, and it will progress the game by whatever action you make. And this function will return um, for value. It will return the next state. It will return the reward, and it will return the terminated, and then it will return info, right? Information. So we have the current state, right? We make this action, you reach the next state, and you also get the reward of your action. So we have all this ready, right? So we can use the update function, right? The update function needs the state, the action, the reward, and the next state. So from here, right? From here, we can say agent dot update, and then you send in the state, you send in the action, you send in the reward, you send in the terminated, and then you send in the next state. So this will update the Q value of the agent. So once you finish the update, you are ready to play the next round, the next turn basically. So when you want to play the next turn, you have to set the state equal to the next state, right? So basically, you just update your current state to be the next state. And then after you finish one game, right? So this will play until you finish a game, right? Play until finish one game. So after you finish a game, you want to decrease the epsilon value, right? Every time you finish a game, you decrease the epsilon value. And then you play the new game over and over. So this is the training loop, right? This is the training loop. So it's gonna play many episodes, and within episode you have this update per turn. So if we run this block, because we use TQDM, when you run this block, you're gonna have oh, did I RL? Oh, did I forgot to? Oh, yeah, RL. Okay, learning rate LR. Okay, right. So it's gonna have this like progress bar to show you like how many. So it's actually play very quickly. So 100,000 episodes should be done in like less than a minute. So we finish 100,000 games, and that's it for the reinforcement learning. Now, what you want to look at as a result, right? You want to look at the reward, right? So the reward will tell you how good the agent is. So you want to plot the reward that you get over time, right? Over time. So what we are going to do is we are going to save the reward, right? Now to save the reward, you have to write a little bit of the variable. So in the training loop, so before the training loop, we're gonna have the episode reward, right, equal to the empty list. And for each episode, we are going to add the episode reward to this list. So at the start of the game, you will set the episode reward to be equal to 0. And every time that you make uh, the action, you will increase, right? You will add the reward to the episode reward. And after you finish, right? After you finish a game, you will append the reward to the list, right? So we will have this variable that keep track of the reward, right? And then we run again. Okay, so we finish. And then we want to plot, right? So to plot, you basically import matplotlib, right? As plt, and then you can say plt.plot the episode reward, right? Uh, so as you can see, right, the episode reward is basically um, I don't know, it's all blue. So there might be uh some error. So let's try to print episode reward for maybe 100, the first 100 number. So the reward, right? You start with -1, right? And basically it will jump up and down between -1 and 1. Because sometimes you lose the game, sometimes you win the game, right? So if you lose the game and you win the game, you're gonna have like this kind of graph, right? Go up and down. So if you plot just the reward alone, it's not enough to actually see the actual value, right? Right. For example, if I only plot the first 10, right? If I plot the maybe the last 10, right? I'm going to have win, lose, right? It's going to go up and down. And when you pack it together, you will get like up and down a lot, right? So to actually make it more readable, we usually use a moving average. So instead of looking at each episode at a time, you look at, well, when you are at 500 episodes, what is the average relate for the last maybe 50 or 500 episode before you? So we're gonna have to make the function moving average, right? Moving average, and this function moving average, basically, it will use the NP convolution, the NumPy convolution, and basically it will multiply the x based on the value, and W here is the window size. So if you pick window size to be 500, it will take the average of the last 500 episodes for that current episode. So instead of plotting the episode reward, we are going to plot the moving average, right? Moving average of the episode reward and maybe 500 window. So the last 500 games, what is the average? So if you plot it like this, then you can see it's more clearly, right? So you have uh, this kind of graph. So depending on the actual play, your result might be different because the style of the game is actually different every time. Like you get different card, you have to make a different decision. So if you can see, right, it's still um, roughly the same, right? If you go toward the end, so you can try to change uh, the learning rate, or you want to change the decay rate, right? For example, if you want to decay faster, right, you can say 0.995, so it will decay faster. And if you put the decay faster, when you train, you can train one more time. It's quick, right? So if you increase the decay rate, it means that it will do less random thing early on. And so we'll have a little bit better, right? You can see it's slowly increasing, but it's never go past zero, right? It will never go past zero. Maybe at some point you have this a little bit higher, but in general you hit uh, something like this. So what does this tell us about blackjack? So -1 means you lose the game, 1 means you win the game, and 0 is the draw, right? And when you learn for a long time, but you wanna like your average barely reach 0, it means that you are likely to lose the game, right? So the hidden meaning is like gambling is bad. So you play blackjack at the casino, um, your return rate is quite low. oh. อืมทำไมเป็นปะเล็กไปแล้วพวกมันไม่ขึ้น Okay, so that's our first example, right? We basically use Q value here, right? So you can actually print out the Q value, um, right? If you want to um, display Q value and in a table, right? So you can print agent dot Q, right? And it's gonna be the default dict. So so each um each parenthesis here, right? You have this is basically this is the situation, right? So our card is the sum is 21, the face up card for the dealer is 7, and we have x, right? So this is the state, and the array here is the property of action, the value of the action. So if you use action 0, you get 0.9 point. If you make 1, then you get 0.08. So you want to uh, always make the zero decision. So the zero decision is basically to stick, right? Because you already have 21, so you will want to stick. You don't want to draw anymore. And maybe we look at the random one, right? For example, if you have uh, you your the sum of your card is 7, and the face of the dealer card is 2, and you don't have the x, you have this score, you have minus 0.09 and minus 0.07. So you will pick this action, right? Because it has the higher Q value. So you want to draw more cards. So that is what is Q value look like inside the agent. Okay, so far so good. Will you be able to write your own agent? So let's try a different environment, right? Different game. So the blackjack, we can use this Q value as a dictionary, right? We can use the Q value as the dictionary because the input space, basically the state space is finite, right? So the finite means that all of these are discrete, right? Your total sum is going to be between 0 and 31, right? There are 32 possibility. The face up card for the dealer will be between 1 and 11, and this one have two values. So each of them have a finite number of value. So the total number of state possible is finite. So when this the state space is finite, you can use Q table, right? What if the state space is not finite? So we are going to use the box 2D, and we are going to play the Luna Land, right? So basically, we have the surface for the Luna, the moon, and we have the spaceship, and we want to land the spaceship in between two flags, right? And What happened here is that our observation space, we have 8 number, but none of them is discrete, right? We have the observation high and observation low. So this is the range of each number, and each number is a real number. So between 1.5 and negative 1.5, how many real number are there in this range? It's infinite, right? You can always find a number in this range, right? You will never run out. So when the when the state space here is continuous, we cannot use the Q table like this anymore because we're gonna have too many states, right? Too many states. So for this particular problem, we are going to use um, neural network instead of the Q, right? We're going to use the neural network. So let's explain the environment first. So in the lunar landing, the action space, you have four. You have four actions. The first action is do nothing. The second action is to find left orientation engine. Basically, it's gonna like you it's gonna have the engine, right? You have the basically you have the spaceship, right? And if you find the left engine, it's going to move to the right, but you also rotate as well, right? And then you have the five main engine. The five main engine is the bottom engine. This is the main, and then we have the right. So we have three engine, right? And then you can for each step you can pick to shoot which engine to turn on. And the observation space, right? You have 8 numbers. The first two number is basically the coordinate of the UFO, of the spaceship. The next two number is the velocity in x direction and in y direction. The next number is the angle and also the angle velocity, basically how much it's spinning. And then the last two is the Boolean, will represent each leg is in contact with the ground or not, right? So it have two legs, like left and right. If one of the leg hit the ground, this value will be 1. If both leg hit the ground, both number will be 1, right? So it's going to be two Boolean value. What about the reward, right? So the reward from moving from top of the screen to the landing pad will be between 100 and 140 points. And the lander, the more it move away from the landing pad, it will lose the reward, right? If the lander crashes, it will receive minus 100 points. But if it come to rest, it will get plus 100 points. And each leg touching the ground will get plus 10 per leg. And in between, if you find the main engine, you lose 0.3 point for each frame that you shoot. And for the side engine, like for the left and right, you lose less, right? You lose 0.03. And if you slope, right, you land perfectly, you get 200 points. So that is the action, observation, and the reward of the environment. Okay, so we want to define the agent to play this lunar lander game, but we cannot use Q value. That is the defaulting animal. We have to use something else, and we're going to use the neural network, right? So in the neural network, basically when you have the state space, right? Right, US, and then you have the neural network, right? You send it each the state to be one of those input layer, and the output layer is going to be the number for each action, right? So it is basically the Q function here, but the Q function is no longer a table. It's going to be a form of the neural network, right? Okay, so we are going to make that. So I'm going to create a new notebook. So I'll example two, right? So again, we want to define the agent that plays lunar lander, and we're going to try to use the same structure, right? So uh, we have to define a class, right? For example, class lunar lander agent, and this lunar lander agent will also have the same structure, right? So you have the uh, initialize, right? The initialize with the environment. You have to write the choose action, right? You still get the state. You have to write the function for update, right? So update, right? Before we have the state action reward of this. Right now, I will write update like this, and then I will explain why we don't have those parameter anymore. And then we have the function for um, so we have the decay epsilon, right? So these are the four functions that we write in here, right? We have the initialize function, choose action, update, and then the decay epsilon. So we have the same set of function, but the detail inside we have to change. So let's start with the initialize, right? So the initialize, uh, we are going to have self.environment equal to environment. So basically we can use the same one, except the Q, right? So we can copy and paste here, but we don't use the Q. So that is what we have from before. But now we have to create the neural network instead of the Q, right? So we want to create what we call Q network. Now to create a Q network, right, we have to create the structure for the neural network. So if you remember from 2 class ago, we write a neural network to um, to do some training from PyTorch. So we are going to use the same thing, right? So we got to uh, define a neural network using PyTorch, right? And to do that, I have to import. So I have to import Torch. I have to import Torch neural network as an end. Import Torch dot optimization as optim, and then we have the function. So basically, uh, this is what I need for creating the neural network. Right? I have the NN, I have the optim, and then I have the function. And if we want to define, right? So we have class. So my network, we have to add to extend nn.module. And in the network, I have to write two functions, right? the first function will have to define the layer inside the network. And the second function is how you compute from input to output. So the initialize function, right? You have the state space, and then we have the action space. So because we want to use this network for reinforcement learning, the input, the input layer of your neural network have to match the number of the size of the state space. For this environment, the state space is 8, right? You have 8 number. So the first layer will have 8 nodes, right? 1 node for each number. And the action space will be your output layer, right? So we can have, oops. So we can say super, and we have self.fc1. So we will start with the fully connected layer. The first layer, like this, the input layer, we have the linear, right? And then you have the state space, and then maybe 64, right? So this is the input layer of our neural network. So we have the input layer, we have the second layer, right? So we have a dot linear, right? So maybe we have 64 to 64, and this one will be the hidden layer. And then we have the last layer, right? And then dot linear, and you have to match 64 to the action space, and it will be our output layer. So make sure that this number, like the output of the input layer, match the input of the hidden layer, and the output of the hidden layer match the input of the output layer, right? So make sure that this number matches. So once you define the layer, right? Now you can define the forward function. The forward function will take the input, right? X is the input. It's basically the state space that you get from the environment. And you have to return uh, the value, right? So we will use the rectify linear unit, right? You take X, right? You fit in the first layer, you get the result, and then you pass in the rectify linear unit, and then you do the same for the hidden layer. And for the output layer, you don't have to use the rectify linear unit anymore. You just use the output of this layer, and then you return X. So this is what we used last time, right? Similar structure. So now that we have uh, the definition of our neural network, we can use this definition in our agent, right? So we have Q network equal to my network, and then you set in the state space and also the action space. And we're gonna have the target Q network as well, right? So why do I need uh, the target Q network, right? So I have my Q network, and my target Q network would be basically the future reward, right? So the Q network is the current network. The target network is the one that you add the reward from the current step, right? Just like when we have this value, right? So instead of writing the future Q value, right, we have the target Q value here. So this target Q value is basically the target Q network. And the reason that I want to have the target Q network is because in the original, every time you make a move, you update the agent, right? Every time you make a move, you update your agent. Now, in this situation, I don't want to update at every step. What I want is I want to create a memory, right? So it's gonna play for some times, and whatever it see it will become a memory, right? And when I want to update the model, I will sample some situation from the memory to train. So not only that I need the target queue network, I also need to have a memory. So the best way to uh, do the memory, I'm going to define the class for memory. So I will define a replay memory. So we have the class for uh, replay memory. So it's basically just a list or an array that keep track of the state, action, reward, and then the next state. Right? If we're gonna keep it right here. So in the replay memory, you will define the capacity, right? Basically how much you want to hold. If you add something when the memory is full, the old memory will go away. So that is the idea for it, right? So we have self.capacity equal to the capacity. And we will use social.memory equal to the DQ. So we want to use DQ. And the DQ here, let's see, I have to import DQ. So from collection, import DQ. So this DQ is basically just a list, but with max size. And when you add something to it and it exceed the max size, whatever come first in the DQ will get pop out. So it will forget the old memory. So we have the function for push, right? So for push, you have the state, action, reward, next state, and then uh, done. So whether or not you finish the game or not. And then you have um, the function for sample, right? And you will specify the batch size. So in the memory, we don't want to train everything. We will pick maybe something at random. Maybe you pick 32 piece of memory from your whole history, and we will use only 32 to train the network. So we will specify the batch size, and then we have the batch equal to the random sample, right? So we sample the memory based on the batch size, and then for each sample we are going to zip it. Basically, we want to take each piece of memory to put into the batch for each of the variable, right? So we have the state batch, action batch, and so on. And we are going to um, return it. So we want to return everything, right? We want to return the state batch, action batch, reward batch, and so on. Um, but we want to make sure that it match with uh, the neural network. So we have to do some conversion. This one you need uh, to convert it to array. So each of the batch, right? We will convert it into the pi array. And for the reward, I want to reshape into -1, right? So basically you change from uh, horizontal to vertical. Oops. And then also for the next state, right? So uh, let's see, can I enter it? Okay. So np dot array of the next state bash. And then for the done bash, also convert into the numpy array. Right. So we want to return all of this. So that is our memory. So for our agent, we're going to have memory. So self dot memory equal to the replay memory. And we will gonna save it about 1000. So we will have maybe many frames per games, but we will save the last 1000 action that we do. And we will sample maybe some of them to train the model. So that is the definition of the agent, right? We have the Q network, we have the target Q network, and then we have the memory. Now we want to choose action, right? We want to choose the action. So for choose action, the way that you write it will be similar before, right? So before in our choose action, we take a random number. If it less than epsilon, we take the random action. Otherwise, we take the best action, right? So that is the epsilon greedy. So we do the same, right? So we say if numpy dot random dot uniform between 0 and 1. If it less than epsilon, we want to say action equal to self dot environment dot action space dot sample, right? We want to sample just one random action. So that is the random action. Now for this action, right? We want to use our network to determine what action we do for given state. So for here, we're gonna say with torch dot no grade. So this means that we don't want torch to compute gradient while we evaluate the model, right? While we infer output. So for here, we have the state, right? So we have to convert the state. So the state that we get from the environment would be from the pi array. But in Torch, right, in PyTorch, we have tensor. So we say state equal to torch dot tensor, gonna be for tensor state dot reshape 1 minus 1. So this will convert the state into the same format to use, because the state is going to be the horizontal array, and then you reshape it into the vertical array. So when you pass into the neural network, is matched with the vertical sense. So we have the state, right? And then we take the Q value, self.Q network. So you send in the state to your Q network. And it will give you the Q values, one for each action. And so you can take the action to be the torch argmax of the Q value. So remember, from here, the Q value is still in torch TensorFlow. So before here, we have the Q value, which is in array, right? So we can take argmax, right? It's still NumPy array, so you can take argmax using NumPy array. But the Q value for this one is the torch TensorFlow, torch tensor. So we have to use the argmax from torch for this type of variable. So we take the argmax and then we say uh, dimension equal to 1 and then dot item, right? So that is how you pick action. And in the end, you return the action that you make. So shoot action is similar in terms of structure, but when you choose the best action, you have to use your network, your neural network to uh, do the calculation. So that is the choose action. Now for the update, right? So for the update, I'm not going to update one step at a time because it's slow. So I'm going to update maybe um, 32 or 64 steps at a time. So in the update function, right, we are going to check if the length of the memory is less than maybe the batch size. So we haven't picked the batch size yet. So maybe we pick the batch size to be 32. So if we haven't played 30 steps yet, we will not update the model. But after you play enough time, you will start update the model. So if the size of memory is less than 32, you return. So there's no update. And if the memory is greater than or equal to 32, you are ready to update. And to update the neural network, right? You sample you sample 32 steps in your memory. So in your memory, you can play 1,000 steps, but you only pick 32 of them at random. And once you pick each of them at random, right, you have to do the conversion again. So you convert the state to a tensor. You uh, uh, change the action batch into tensor. So we change every batch variable into a tensor. For action, you're gonna need unsqueeze. It's just for safety, but the rest you just only need to convert to. So we have all these batch, right? You have state batch, you have action batch, you have reward batch, you have next state batch, and then we have done batch. So now that we have all the batches, we can perform the update at the same time. So how do we train the model using these 32 memories? So we start with the Q value. Let me move it down. So we start with the Q value first, right? So we have state, we have next state. So we're going to use the Q value using our Q network and the current state, right? So when I send the batch, it will calculate the Q value for every memory inside the batch, right? So this will be very fast. Like you don't have to do one step at a time. You can do 32 steps at a time. And then you say gather one action batch. So this Q value, right? This Q value is going to be the result of each of the state, right? So you have the Q value for the current network. And then we will calculate the next Q value, right? So the next Q value is basically you use the target Q network, but you use the next state. So you have the Q value of your state, you have the Q value of your next state, right? So you have the next state bash, and then you also have the maximum, right? You take the maximum, keep the mention equal to true, and then you can do 0 and then dot detach. So you take, so in the first one, right, for each of the state bat, you have the Q value for all of the action, but dot gather here, it will only pick the Q value based on the action that you actually do. And then it will put into the Q value. And for the next Q value, again, it's going to send in the next state, right? The next state is going to have the Q value of all the action for the next state. But we only take the maximum. So we take, for all of the action you have, the first dimension is going to be of the action, you want to take the maximum, and then you will get the next Q value. So we have the Q value, you have the next Q value, right? If you look at this, so this is the, so this is the Q value, right? The Q value is here. This is the next Q value, right? So this Q value is the next Q value. And we want the target, right? So the target Q value is going to be the reward, right? Plus 1 minus done bash times self dot gamma, the discount factor, times the next Q value. So this equation is the same as basically this equation. Target Q value equal to reward plus gamma times the future Q value. So we have the target equal to the reward plus self gamma times next Q value. The 1 minus bash here is the short form for this if statement. So instead of writing if statement here, I condense it into just one here. So if we are done, right, if that memory is the last turn of the game, the done batch will be equal to 1. So 1 minus 1 is 0. So there's no future reward, right? But if you are not done, your done batch will be 0, and this will be just 1. So you just add gamma times the Q value to your target Q. So we have the target Q value. We have the Q value, right? We want the Q value to be the target Q value. So from here, what we do here before, right? We take the difference and then you time the learning rate and then you add it, right, to the current value. Here we can't do that directly. Why? Because we have a network, right? We have to update the weight inside the network. So what we have to do is we have to compare the Q value here and the target Q value here. And you want to find some loss function, right? Loss function between these two values, and you want to update. So we are going to use the loss function. So we can use the MSE, the mean square error, from actually we have to use the NN dot MSE loss, and then you send in the Q value and then the target Q value. So this will compute the loss, right? So it's basically the difference between these two, but in the MSE sense. And we're going to have the optimization. We haven't defined the optimization algorithm for our neural network. So we have to say self.optimizer, right, equal to the optim dot. We're going to use the Adam, and then we'll send in the parameter for the network. And then we are going to send in the learning rate, right? The learning rate will be self.learning rate. So this optimization, it will optimize the weight so that this Q value will become closer to the target value. So for here, we actually do the optimization ourselves by subtracting them and then time the cell out and then add it. So this is our own optimization. But because this is more sophisticated, we have to use the optimization. So in here, after we calculate the loss, right, we are going to say self dot optimizer dot zero gradient, and then we will say loss dot backward. So this loss dot backward is going to do the backward propagation for the network. So after we do the backward, we can say self.optimizer.step. So it will perform the backward propagation on the weight or the parameter that we set into the optimizer. So after we finish, right, and then, so this one, we can do self. So we have this update, right? So we have this update, and then we have another update, right? So we have update target network. So this target network, because we have two network, right? We have Q network and then we have target Q network. The Q network is used for the current state. The target Q network will use for the next state. So after you optimize your Q network to be the current state, to be the next state, right? You basically copy the Q network into the target Q network, right? So basically this function will copy Q network to target Q network, basically. Oh, and then we haven't do the epsilon decay, right? So this will be, I think, the same code for the epsilon decay. So you can just copy the same line of code. And when you want to decay the epsilon, it will also depend on your algorithm, but that is the definition of the agent that you would play the Luna Land. So for a recap, right, the agent need initialize, you specify the environment, you specify all the parameters, you have the two network, one is Q network, one is target network, you have the optimizer, usually Adam, And then you have the memory that will save the replay. You have the function choose action, and then you use the absolute greedy policy to take the random action, or you take the best action. And then you do the update function. So now that we have everything, right? We have the network, we have the replay, we have the agent. Now we are ready to play the game. So to play the game, um, so invalid syntax. Oh, small c. So to play the game, we have to install two packages because the box, the box 2D environment is actually not part of the initial import, right? So we are to do, so we want to install the box 2D. So we have pip install swig and also pip install gymnasium box 2D. So we have to install these two packages for this game. So while we wait for the installation, we can work on the code for playing the game. So to play the game, we will import gymnasium as gym, right? And then we kind of do the similar structure, right? So here we create the environment and create the agent, right? So we do the same. So we say the environment equal to gym.make, and then we have the Luna lander. This is the third version, version 3. And then we create the agent equal to the Luna lander and the environment. And now that we have environment and we have the agent, we kind of do the same, right? Do the same. So what is the same? So we have the training loop. You go to play each episode. In episode, you have many steps. In each step, you take action, you update, and then you go to next step. So here we can go to the training loop as well. This one I'm going to use the TQDM as well, so we can see the progress. So we're going to import TQDM as TQDM, and then we have the for episode in TQDM range. So and then agent dot number of episode. So right now, our number of episode is actually 100,000, and because this game is longer than the blackjack, we're going to decrease it into just 1,000. We want to make it quick, so we change it to 1,000. So we change this into okay. This to be reward bash, right? Okay. So we want to play just 1,000 episode. So for each episode that we have, right? So we start with the state, right? So we have the state equal to the environment dot reset, right? So the same thing, right? Same thing here. And then we're gonna have the terminated equal to false, right? Because we just start the game, it's not over yet. And if we want to plot the episode reward, we can also say episode reward to be the empty list, and then we can set the episode reward for this episode to be 0 at the start. And then we will say why not terminate. So we play until the game ends, right? And then we have action equal to agent dot choose action based on the state. And then we have next state. We have the reward. We have the terminated, and then the other two that we don't care about, dot step action, right? So we take action, we get the next state, we get the reward, and then we get the status whether or not we finish the game. And now come the difference. So before, after you perform the action, you update the agent, right? For this one, we are not update the agent yet. What we do is we add, right? So we have agent.memory dot push, right? Put the state, the action, the reward, the next state, and the terminated. So basically, we save the current step into the memory, and then we can do the update. So we update at every step, but during the step, we update from 32 memory in the past, right? It's going to change over time. So it's not just the last state that we just play, but any random number of 32 states that we have. And then we can move on to the next state. And then we add the reward into the episode reward so that we can plot it later. Right? So we have episode reward dot append episode reward. And then after you finish, right? After you finish the episode, right? For each episode that you finish, you are going to update, right? So we have the agent dot update target network. So your queue network will be updated at every step, but your target network will only update at the end of the episode. Okay, so that is the difference. And sometimes you want to save the model, right? Maybe you train for 200 and then you want to save the model so you can check later, like you can compare how the model does at maybe 200, 400. So we can have some code to save, right? So save a copy of the agent every 200 episode. So if the episode mod 200 equal to 0, then we can save torch.save agent.queue network. So we're going to save the queue network, the, the dictionary of the queue network. And the file name is going to be .pth. It's called PyTorch something. So this will save into a local memory, the local drive of the Colab, and then you can download it in your computer, and then you can load it later. So we have we save it, right? So normally it's going to be, because it's going to be at every 200 episode, the last episode number. So let's see. So we have episode plus one maybe, because the last number is not going to be 1000. It's going to be 999, and it will not save. So we'll say plus one here. Okay. So it's going to save at 200, 400, 600, 800, and 1000. Okay. So we can run this. Oops. Uh, oh, I forgot to define the name tuple, right? Because basically when I return, uh, where is it? When I return here, I haven't import. Uh, so I need to import random. Right? I forgot to import random here. I also forgot to import numpy as np. Um, and then I have for collection, I have to import DQ, right? Because I use the DQ for the replay. And then I have import name tuple so that I can define uh, the transition equal to the name tuple. So I have to have state action, next state, and then the reward, right? So have this for value, so that when I return, when I add this, it had to have done as well. Right? It to be state action reward next state done, state action reward next state, and then done. Okay. So this will have the definition. So when I append this, it actually understand this name. Okay. And hopefully this work. Argument size failed to unpack the object. Type must be tuple, but got box. Okay. So maybe I need to change the way that I get the observation space because it's different variable. Uh, let's see. Okay. So the observation space, it gotta be dot shape 0, and the action space is gonna be dot end. Okay. And then for the network, I think I forgot to convert it to float. Okay. So with this definition, okay, so it should work now. No, the module is not callable. Agent.num episode, agent.num episode. For episode in, what is the difference? It's the same, right? Or maybe I forgot to have the number of episode. Yeah, I have the number of episode here. Did I? No, no. In it. Oh, env. Okay, okay, okay. Okay, so mhm, the object module is callable. So I have the class Lunar Lander. I have cell.environment. I have state space. I have action space, right? And then I send in for my network. I have my optimizer. I have my memory. Uh-huh. So it doesn't seem to be incorrect, but I'm not sure why it error in this step. Did I forgot to import something? So let's Gemini explain the error to me. So, oh, so I import TQDM. Wait, but I also import. Oh, it's said to be from TQDM, import TQDM. Okay. Okay, I import it. It's incorrect. Okay. So now it start playing, finally. So it's going to be playing about 1,000 games. It probably take about 5 to 10 minutes. And at 200 episodes, it's going to save a file. So when you are doing uh, like a lot of machine learning, it's important to save the model every time you make changes, so you can always have the backup, right? So you have agent at 200, right? So it's going to be gibberish. It's basically a binary of the agent. So while we wait, let's create the code for plotting, right? Basically, we have the code for plotting already. So we just copy and paste. Now for this one, because we only play 1,000 episodes, we're going to set the window to be maybe 20, like the last 20 games instead of 500. And then when it finished training, we can do the plot. So now we have 300 episodes already. So it should finish very soon. Um, Depending on your subscription, if you're not pro, it might take longer time than mine. Yeah, very soon, very soon. Mm. So in the assignment, make sure that you do it ahead of the time, because it's going to be at the time for the training the model that's going to be very slow because of the reinforcement learning. So have anyone read the description of this game? So you know the objective, right, of this game? Okay, that's good. Okay, so we finished 1,000 episodes, and then we can do the plot. Right. So the plot again, so let's see. So it's really different from when I trained earlier. If I set to 50, so they are going up and down, right? So it doesn't look like it's learning. Let's see. Even though I do the same thing, maybe there's something different. I see. So my original code doesn't have this line, but it should have this line. So let's try to update the target network every time you do the update. Let's see if it make a difference. So it's not always the case that like there's like you can switch thing around. So we have the update and then the target network. So I want to update and then update the target network right away. Let's see if it make a difference. And then we will move on, whatever the result we get. So while we wait for the training, we will create the code to save the animation, right? So you want to see how the agent do, right? Right now you only see number, but you don't know the behavior of the agent. So we want to save basically a GIF image, GIF animation image. And to do that, we will have to write two functions. The first function is called load model or load agent, right? So we save all these agent. We have to load the agent and then make it play one game, and then we save the replay into image. So we have load agent. We have the agent path, right? Or maybe we just uh, say the episode number, right? So we have the agent equal to the lunar lander agent, the environment. I think you have to send the environment as well, right? And then we're gonna have the agent dot uh, Q network, right? Dot load state dictionary, and then tosh dot load the path. And when you choose the action, you only use the Q network, right? Right. In the choose action function, right? You only use the Q network. So you only need to load the Q network. You don't have to load the target Q network. So when you load it and then you return the agent. And so we have the agent. Let's say I load 100, right? I have to create the environment first. So it's gonna be the environment equal to gym.make the lunar render v3, and then I specify the render mode to the RGB array. So setting render mode, it will save the image for us. So after I play, right, I load the agent, and then I want to generate, right, the GIF image. So I will create the function called uh, generate GIF image, right? So we gonna send the model, right? So we have to send the agent. We send in the output file name, right? Actually, the agent, the environment, and then the output path. right? And to generate a GIF image, I'm going to use the Pew library. So for Pew import image. And the way that you play the game is the same as the step loop, right? So we start with the state equal to the environment dot reset, right? And then for each frame, we start with an empty frame. Um, and then we say why not terminate. We have to terminate equal to false. So why not terminate? Right? So we keep playing. We have the state uh, tensor, right, equal to torch. Actually, I don't need to do that, right? I can say action equal to agent dot choose action given the state. And then I say next state, right, equal to terminate, and then the environment dot step action. So you send action to the environment, and then for each frame you append the render. So it's going to be image dot from array dot env dot render, right? So you save each one, and then you have the state equal to next state. And then at the end, you save, so frame 0, you save to the output path, right? And then you save all the image in the animation, and then you can set the duration and set whether or not you want to loop. So this duration is in millisecond. So it's gonna have like 40 milliseconds for each frame. So now that we have that function, right, we can say generate if you say in the agent, say in the environment, and then uh, maybe Luna dot give. So I load the agent at 1000 iteration, and then I play a game, play one game, and then generate the GIF. So let's see if I finish training. So I finish training, and then I do the plot. So the plot doesn't change much, uh, but we can try to play one game for 1000 iteration and see how much it improves. So at 1000, right, you can double click. So it's gonna crash, right? Basically, it crashed. So it's still not very good. And one of the things that we can improve is that, so right now in the training room, right, you play until you end the game. But sometimes the game can go on forever. They can just stay in the air and then keep shooting the engine and not landing at all. So you can kind of like cut it short by saying that, well, we will do it when it finish the game or the length of the episode reward. No, I have to play. Let's see. So I have to have the number of step to be 0, and then every time I do the step, I add 1 to the number of step, right? So while terminal and the number of step is less than maybe 1000. So if it play more than 1000 step, I just start a new game, right? Because it never land. So we better start a new game. So it should be a little bit faster to train, right? And then we will see the difference. But while we wait, so you can do this for like different iteration. You can say for all type of agent to get the GIF animation. So that is how you use neural network in place of the Q table, the Q value table. So it's a lot of work to actually build one. Okay. So while we wait for this to finish, I'm going to move on to our assignment, right? So in our assignment, we are going to play the game is basically a resource gathering game, right? So we have a base, right? Basically the building over here, and then we have a worker, right? And the objective is to stay alive until the end of the game. And the worker is going to like move and then collect resources from around the world, right? The world will be the grid. So in this challenge, um, the first thing that you want to get started, you if you go down, like, so if you read all the uh, information about the game, so you should know the rule of the game. So I will leave it that in your own time. But the starting code, right? If you want to start, you go down toward the very end, right? You have the getting start one. Now, in the getting start section, you have two templates. You have the quick start template and you have the tutorial template. So I want you to start with the quick start template first so that you can run in your own. So if you click on the quick start template, it's going to open the Kaggle notebook. You can copy and edit this notebook into your account and then you can edit it. For me, I'm not going to use this one. I'm going to copy line by line into the collab. So you can see how you can run um, this game in the collab as well, not just on the Kaggle. Because in the Kaggle, you just run each block, basically. So the first thing, I'm going to create a new notebook. So we have RL, example 3. So in this new notebook, I'm going to follow the exact same sequence that they suggest in the Kaggle notebook. So in the beginning, I have to install the Kaggle environment. So I do the same, right? The exact same code. So I do the pip install, right? So after I install the Kaggle environment, I can move on to install, to import the make and also the JSON. So the game result, the game replay will be saved into the a JSON file. You can save this replay and then open in any web browser. So I'm going to copy this block of code and I'm going to put it into the next into this block. And if you install correctly, you can import, like you can make the environment. So remember in Gym, right? When I create the environment, I use the function make, right? I use the function make here, right? Gym.make, and then I specify the name. So this one is similar. I use the same function make, but it used the Kaggle environment, so there's no gym.make, so just make. And then the environment will be named Lux AI. And then you can have the different configuration. So the seed here, you can change the seed, you get a different map, basically. The map will be randomly generated. So if you want to try a different map, you can change the seed, right? For example, I change it to um, two of to into this class number. So after I create the environment, I can say steps dot equal to environment dot run, and this will play the game. This function dot run is going to play the game, and because it's two-player game, you have to send in two player to play, and this is the name of the player. In the environment, they have the simple agent install it for you. So if you want to run the default agent, you can just simply put the name, right? The name simple agent. So basically, it use the same agent as player one and player two to play the game. So if I run this block of code, it's going to create this game environment, and then it's going to play a game. So after you play a game, you want to visualize what happened inside that game. And we have the code called render, right? So we have render function. So we say environment.render, you set the main into IPython. So the IPython will work for both Kaggle notebook, your Jupyter notebook, if you install locally, and also the Colab notebook. So the mode should be IPython. And then you specify the width and the height. So let's say I have 600, and then the height would be 400. So I want it to be small, so it fit my screen. So if you run this code, it's going to generate the replay for you. So in this map, right, you have two players, blue and yellow, right? So blue is here, and then the yellow is here, right? And then you can click play, right? So it's going to play, right? So we have the worker move to the wood to collect wood, and then come back to the city to generate the fuel. So that is what the simple uh, agent does, right? It has uh, no fancy things. Basically, it moves to the closest resource. It will collect the resource, and then it will come back, right? And then now it becomes the night. So during the night, like the fuel, right, inside the city is going to be used to generate the light to keep you alive during the night. So that is how you play the game, right? To play a game. So that is okay. Now you want to create your own agent, right? Right now you just use simple agent. If you want to create your own agent, you have to write your own code. But they have provide a sample, right, of the code to write. So in this step, right, you have they have the copy function. This will work if you use the Kaggle notebook. But if you use Colab, you use your local Jupyter notebook, this will not work. And the way to work it locally, you go to this one, go to this folder, right? So you go to this folder. It's going to be the GitHub folder. And then you simply download. Let me find a download button. So we have this one, right? The simple.tar.gc. So you click here, it's going to download the sample for us. So in the folder, I can try to extract. I extract all into the simple. So in the simple, you have agent.py, you have main.py, and then you have lux folder. So the way that you want to use it in Colab is that you have to create the same structure, right? So for here, you create a new folder called Lux, right? You have to create for Lux. And then from here, let me, first thing you copy the main to this folder, to the outside. And then in the Lux folder, right, you have all these file. You upload all this file into the folder, Lux. So your file structure should look like this. It should have main.py in the front, and then in the last folder you have this file. The reason why I cannot just upload the folder because it doesn't allow you to upload a folder. So you have to create a folder and upload the file inside the folder. Okay. So now that we have all of these files in the directory, so you have to do this every time you open Colab because this is a temporary file. It will be erased when you close this page for a long time. All right. So what I do here is basically I copy this line. So if you use Kaggle notebook, you just run this line. But if you use Kaggle or your Jupyter notebook, you have to do this. Okay. So now we are ready to write our own agent. So when you want to write your own agent, there's a command called write file. So whatever you write in this block of code, is going to be write into a file called agent.py. And this will be part of your submission, right? You have to create the agent.py. And inside the agent.py, you can start writing your agent class. So similar to what we wrote here, right? What we wrote in the agent class, right? We have the initialization, we have choose action, you have update. So we have to define a similar thing. So we start with importing all the Kaggle environment. So I'm going to copy this import to here. So don't worry about this switching line. It will be resolved once it actually understand that we have the last folder in our directory, but it will not give you the error when you run it. So just leave it at that. So we import all the important. So we have game, we have cell, we have resource type. So it's basically the game information. And now we will say the game state equal to none. This game state is basically our environment. So remember that this game doesn't give you the state, the observation state, the reward, the action state for you. So you have to create your own. So we start with the game state, and your agent, when you define the agent, right, you have to give it the observation and the configuration. And then inside the agent, you have the global game state. And in the agent class, right, so when you define the agent, it's basically a function. Right? Your agent here is a function. You get the observation parameter and the configuration, and you want to return the action. So when you write the choose function, the choose action function, right? So basically we want to write this function. We want to write the choose action function. So here we have the game state. Right? We have the game state. And then this is the game variable. And do not edit this part. And the thing that you want to edit is the last part, right? So you start with empty action. The player, this is your player ID, this is your opponent ID, this is the width and height of the game, right? So you have all this information. And then you return the set of action. So right now, my action is empty. So basically what this agent do is it does nothing, right? Because you doesn't send any action. So we will try this one first to make sure that everything run correctly. So we define this agent, right? This agent function, right? It's gonna receive the observation. The observation is going to be, the object, and then you want to return the action. So when you run it, it's going to write the agent.py for you. So you are in your folder, you should have main.py, you should have agent.py, and then all this last folder. Okay. After you define this agent, you can save, right? You can save uh, for submission, right? Using this code. So we have you have to save it into the tarball, right? So all this thing. So uh, with this, right? You run this code, you will have a new file called submission.tar, and then you download this file, right? So once you download this file, you go to the assignment, you submit the agent, and then you pick the file that you just download. So submission.tar.json. And when you upload, you want to type some description. So the agent does nothing. And then you can click submit. It's going to submit the agent to the competition. It's going to be a while. Maybe it takes like a few minutes. So basically what you send, it will play the game against itself first to check if your agent doesn't have a bug before it will play with everyone else. So the opponent is going to be everyone in the class, right? If you submit early, your game will play with like author who already submit the game. So right now there's no submission, but I expect everyone to submit as soon as possible. So when you submit, this is the example of your finished submission. So the submission, you have a score. It's basically your rating, your number for rating. So right now, there is no other competitors. It's just yourself. Your starting score will be 600. And when someone upload a new agent, your agent will be play against the new agent. And if you win, you gain some rating. And if you lose, you will lose some rating. So your number will go up and down. So you can submit many agents for yourself. So right now it's only just myself. So it's only going to be 600. But if there are more submission, so we have submission here from someone. So it's basically it's going to play with authors at the end of the day. Okay. So I think my submission, because I'm the host, my submission will not be played against someone who already submit. So it's going to be like everyone else in the class to submit. So that is the empty agent. And if you want to make it more smart, there is a notebook in the tutorial, right? This template for the tutorial. If you open the tutorial one, the code will be exactly the same except the part when they write the agent, right? So when they write the agent, right, they have the function called file resources. They have the function for file process resources. So basically, what this function does, right, is find all of the resources on the map, right, and then it's gonna save you in the list of cell. And then find process resource, right? You give the position, you give the player, and then you give the resource tile from this one. It will return the closest resource tile. And then when you have these two functions, you go down in your agent, right? For each unit, in your in your player, you can check if it's a worker and it can act. If it's a worker and it can act, right? You can check if there are space in the cargo. If there is a space in the cargo, you move to the closest tile. So that is the entire algorithm that they have. So we can use this to just move the agent to the closest, and that's all. That's it. It's going to survive a little bit before it dies because it doesn't go back to the base to exchange the resources for a fuel. Right, so this one will right, it's basically going to move to the closest resources and stay there until the rest of the game because that's what you tell it to do. So for us, right, if you want to use um, the reinforcement learning, right, what you have to do is for each time it call this function agent, you have to first convert observation to observation state, right? Because right now observation, right, is basically the game state, right? So you want to convert the game state into the observation state, and you can design your own observation state, right? For example, your observation state might have maybe 4 numbers. So the observation state can have 4 numbers. So the first number would be maybe one of the unit, right? So if I use the similar structure here, right, for unit in player.unit. So for unit, right, in player.unit, right, I check if the unit is a worker, right? Is it is worker? Okay, is worker and can act, right? If it's a worker and unit dot can act, then I can construct the move, right? I can construct the move. So here, okay, so this one will be choose action. This one will convert the game state. So the game state is also depends on how you want to create the state. So let's create the state inside. For each worker, you have a different state, right? So we create the state. So the state we're going to have let's say the state have only two number, which is the location of the agent, the unit. So your state should be the unit dot position. So gonna be unit dot position. And then if you use, let's say you have your queue learning, you can define here, right? You can define your queue table, right? Basically, this is the queue table that you have over here, right? So you can define it here to be like this, right? So, but you still have to import from collection, import default dict, and then import numpy as np. Right, so you can define the queue table for your agent over here. So this one will not be self. So inside here, you have to specify the action. So in the game, right, how many action can we have for the unit? So for the worker, you can move, you can pillage, you can transfer, you can build a city. So let's keep it simple. Let's try to just move the worker only. So in move, you have 5 directions: north, east, southwest, and the center. So we can have uh, this to be 5. So there are 5 actions for this worker, right? So we have this queue table for worker. And for here, I have the state, right? And then I can say, so we have the state. Now in the choose action, I take the state, right? I put it in the queue value, right? And then I take the argmax. So I can do the same, right? So I can say action equal np.argmax, right? I have the queue table for worker, and then I send in the state. So whatever reaction that you get, you want to add this action into the set of action. And this action is going to be a number, right, from 0, 1, 2, 3, 4, because you have 5 actions. But this number is meaningless in the game. So you have to convert this number action into the actual command for moving the unit, which is the unit.move. And then we have the constant for the direction. And then you send in the action for the direction. So the direction here, basically 0 will be north, 1 will be east, 2 will be south, and so on. So you can send this action over here, right? So after you send the action, right, and then you cannot return the action, right? So this is how you would use the queue table to make move. Now, if you want to update, right, if you want to update the queue table, what do you need to update the queue table? You need, so if you look here, in the update, you need state, you need action, you need reward, you need terminate, and then you have next state, right? So you need to have 5 of these. How many do we have now? We have state, we have action, do we have reward? No, not yet. Do we have terminate? Do we have terminate? So we don't know if we have terminate, but the game state should tell you if it terminate or not. There will be a variable for it. So let's say we have terminate. What is the next state? We don't have the next state. So we cannot update right now because we don't have all of the information. So what you have to do, you have to create a memory because um, in this one, right, you move, you constantly playing. So you have to save your own memory so that you have the current state, you have the next state, right? So at the start of the game, not only that you have to have a queue table, so you have to have the previous, let's say, um, the previous state. And the previous state at the start is going to be none because you don't, if you start the game, then you have none. Actually, it has to be a global, right? So you have to have the previous state equal to none. And then you have the, oh yeah, actually this one, right? You have to define it outside. You have to define it outside, right? So you have global for the previous state, for the queue table for worker. Here, okay. And then you would have the maybe previous resource previous full, right? And then we have previous full. So right now we have this state and with action. So we need to have a lot of things, right? We have to have the previous action as well. Okay. So we have to save a lot of things, right? So previous action. And when you do the state, right? You do the state here. So basically, you have the action, right? So when you reach this one, you actually have the next state, right? So when you have this one, right? So you have to check if the previous state is not none. If it's not none, you can update the queue table, right? So in the queue table, right? So now you have previous state, right? You have previous action, and you need to define the reward. We don't know yet. And then you have the previous state, and then you have the state, which is basically the next state, right? And then you have the terminate. So you have all these variable, right? And for the reward, so maybe you can define the reward to be, I don't know, game state, should be the player dot. So what do we have for the player? Let me go to the API real quick. So the player should have the full, right? No, we don't have the full. So we have the full should be in the city, right? No, the city tile. The unit. Oh, okay, the city, right? So in the city you have the full. So in the game state, in the game map, in the player, you should have cities, right? Okay. So for all the city, right? For city in player.cities, right? You can have like you can start the reward to you start the full to be equal to 0, and then you can have the full plus equal to city dot full, and you can define the reward to be equal to the full of this iteration minus the previous full, right? So if your full increase, your previous action actually have a good impact on the game. So you can define your reward like this, right? So you can define your reward depending on what you want, right? You can do the sum of the full, the full, the number of units, and so on. And so once you have all this, right, you have all these variable, then you can use this update function. You can use this update equation for the queue table. So this is when you play the game and learn at the same time. So at the end of your play, you want to save your queue table. You want to save your queue table into a file. And when you want to submit, right? When you want to submit your queue table, you will no longer have all these update. You will load the queue table that you save, and then you will use the queue table to make the decision. So when the agent that you submit will only have only this, but the agent that you train, you will have all this information about the training part. Okay. So that is how you would use the reinforcement learning in this type of environment. So you have to kind of integrate the learning part into just one function. All right. So any question about the assignment? It's gonna take a bit of time to get started. So make sure that you submit just empty agent first and slowly build up. Right. You can uh, try to understand the the tutorial part, like what it does. So here they don't use machine learning. Basically, they just come up with a strategy and just write down their strategy. Okay. So you have uh, about like 2 weeks and a little bit to finish it. I think it's after the exam. Yeah, it will do after the exam. So you have a little bit more time. So if you have any question, feel free to uh, contact me in Microsoft Teams. If you run into like bug or error, you can just send the code to me and then explain what the error is. Or if you use the Colab notebook, you can also share the notebook so I can run myself and see what is the error. All right. Okay. So I guess that is for today. We actually does a lot of code today. I will upload all this file to the course so you can take a look later. Next week is going to be our last class, and then we will have the exam afterward. So I will see you next week.